so I switched to English. Because it's much easier, and for the international people here on the line, it's much easier to really think about exactly what we need to do. So Katrin and Thomas, thanks a lot for the kind invitation for me to talk here about what BASF is doing and what drives sustainability. And the title of my talk actually is Innovation Drives Sustainability and Sustainability Drives Innovation. Very much close to what the NEULAND has, nachhaltige Innovation. But which came first? Think about it, innovation or sustainability? I think they go hand in hand. And I want to show you a little bit on the journey. I'll take you through exactly what that means for a company like BASF. Okay, so let's dive in and see exactly what I can tell you about. I'll talk a little bit about BASF, how this fits into our structure. I'll talk a bit how we do research, and specifically the research that I am responsible for, and then I'll go towards sustainability with a few examples out of the portfolio. And obviously I cannot speak about everything at BASF simply because BASF, and you see it on this chart here, is so large. I mean, we cover the area right from the upstream chemicals, petrochemicals, go downstream, move to intermediates, go into surface technologies, human care and nutrition, all the way to agrochemicals. And you can imagine this is a great playing field for sustainable chemistry. And this is more or less what drives us. And this is exactly the breadth that we have. And it's, I think, a very sustainable business, to be honest, if you look at it. I mean, we had a good year in 21, nearly 80 billion euros of sales out of this business model, if you like. And the question now is, exactly what do we do in the future in terms of sustainability? But let's first reflect a little bit on the past, and Thomas mentioned it already. It goes back all the way to, for example, the Haber-Bosch process, which of course is a key technology that more or less is driven by sustainability, but it goes even earlier to the roots of BASF with the colorants and dyes. But what you see on this picture actually is a line, and this is only a selection of different technologies, one after the other, from base chemicals to fine chemicals to agrochemicals to products that serve for insulation like the neopor, or even high-end catalysts that you will find at the tailpipe of your automotive if you look at the four-way conversion catalyst. So it's actually the breadth. And you could argue, is this all sustainable? Well, I would answer the simple question with yes, because otherwise BASF wouldn't be here anymore. It's a sustainable company. But I think the question now is not to say we can relax and say we had a great run of wonderful innovations. What is there in the future? But before I go into what, I want to talk a little bit about the how. And one of the things is, in principle, how do we structure our research and what is driving us in research? And this simple picture actually tells you exactly what is in the focus of everything we do is our customers, but of course behind that are our consumers. And it is the operating divisions, you know, you saw them in this colorful chart, upstream all the way to downstream, who actually serve them, sales, marketing, production, with products and processes. And what is important now is this red line, very closely linked to this is group research, what I'm currently responsible for. A few words on that in a moment. But the driving force of what we do is actually we collect knowledge with KIT, for example. We work together with other academic institutions, we work together with startups, we work together with other companies, and actually focus brainpower, knowledge towards industrial research to bring it to our customers. That is in principle the simple business model of what we do. And you see by the numbers that we invest in this, over 2 billion euros, and we play across this field because we are so broad, and 10% of BASF's employees actually are in the R&D space. It's a very strong signal also that we intentionally invest into the future. I want to talk just briefly about group research simply because also as structures change, also in KIT, for example, also the BASF sometimes restructures itself. And we do that all the time. We ask ourselves all the time, do we have the right R&D strategy? And I just want to highlight here, let's say the last 7 years or so. And what you see here is that we constantly ask ourselves the question, are we set up correctly in terms of this core of BASF? And you see here we want to be global. For example, we had 3 research divisions only 7 years ago. We had them, by the way, historically, and they were all located in different regions. We had, for example, clearly a driver that you all know is a new innovation approach, how to really move digitalization. So we combined the forces of all BASF people working in R&D and in innovation, just as one example. We had a few ideas about driving BASF and the mindset specifically on output, because we put a lot of money in. You saw the 2 billion, but we are looking, of course, for products and processes that come out. So we had a whole endeavor there. Then we had a corporate strategy. You already saw that we work on sustainability, but it's also business-oriented. And business orientation is more or less where our research has to find its home, and that's why we combine the business and the R&D topics together with innovation strategies. And finally, this was called Project Unique. We decided to ask ourselves, do we have the right structure really driving the business? And that then led to the fact that some of our R&D, specifically the D units, moved closer to the business, and then we merged together all the historic and legacy different R&D sites into one group research, which of course is immensely large as a company, as BASF, and you can imagine this is more or less the new setup called group research that I'm heading. And what does it look like in a snapshot? I mean, if you take all the research of BASF together, first of all, you see here on the chart, it's global, maybe different to a university like KIT or other universities. We're all across the globe, starting from San Diego, where we have our enzyme technology, all the way to Shanghai. That is our footprint. We have many scientists, employees, technicians, 3,600 worldwide. So I could say we do research 24/7 across the globe. Really good. We are responsible for a third of BASF's whole BASF budget. That's a lot of money that we spend. 600 million a year is around 2 million a day. And that's a lot of money that is going consistently into research. And we spend a lot of money to maintain it. Look at the CapEx, but we also have sales, because we have companies like high throughput experimentation that actually sell R&D to third parties. And then we asked ourselves how to structure it best. And Thomas and I were already philosophizing on what is really needed is an integrated approach, and this is exactly what we have done here. So we have the core facilities of what we do: process engineering, everything to do with chemical synthesis, process catalysis, homogeneous, heterogeneous, biotechnology, the enzymes I mentioned, but also functional polymers and material formulations, because many of our products go out to customers as formulations. This is the core. It's not everything here, but it combines more or less the core of what we do, and we have 2 units working on this. One is upstream and one is downstream. They each have around 750 people. But it wouldn't work, and that's, I think, a very important point, without the other units that we have here that are called scientific enablers. You see them: analytics and material sciences, toxicology, ecology, digitalization, automation. We keep, and we have this as one unit. Over 200 people are working here. Pilot plants and technical services. We are scaling up things. 500 people work there. And I already mentioned the high throughput experimentation. And it's all about the coherence and working together of these units. These are not silos. They have to work together on the problem. So we want to mix the competencies across this field to tackle the sustainable topics that we are looking at. And maybe one last word: how does industrial research work? It's very simplistic here, but in principle, if you work along the cycle, you need an idea, you go to the lab, you go to a mini plant and scale it, the pilot plant and production plant. Now you would say, well, that seems a bit long stretch to go, and it would take a lot of time. And I would say this is old school. So what we are really working on, and this is where digitalization comes in, is to do molecular modeling, to work out how our plants can be more efficient without doing the experiment, and designing plants much earlier and taking shortcuts, if you like, through data science integration, but also digitalization. So going from lab scale directly to pilot plant, going from mini plant directly to production plant. This is in principle where the music will play in the future. And it's all about collecting the data that we have and doing, I think, high-end modeling. That's also why we have a supercomputer. That's one part. But do we have, as a company, have to do everything ourselves? The answer is clearly no. We like collaborations. We like partnerships. We work together with, let's say, companies who are very proficient in doing high-throughput experimentation on chemical synthesis. We don't have to do everything in our labs if we do work for new active ingredients for agro, for example. Or we are in the scaling process where money is really important. We are talking about triple-digit millions if we go into piloting. Then we like to partner. So certain processes, we say we join forces. Someone brings in the catalyst, someone brings in the process know-how. We do this together. Risk shared, but also the gain shared. And finally, of course, we are not shying away also from in-licensing. If our startups have good ideas, why not take them? I mean, exactly that point is important because a startup does not maybe have the cash, the power to really scale things up. And that's where we like to work together. So this is the how to do research, and maybe just on a very high level, exactly what we want to aim at with the group research. Now I shift gears. Let's talk about more or less what this NEULAND is about sustainability. Perfect fit. We create chemistry for a sustainable future. I think it's a wonderful logo we have and a wonderful mission statement or purpose statement, because this means that every experiment my group does with the 600 million should refocus on sustainability. And if not, they shouldn't do it. And the question is, I always challenge everybody, is your experiment really working on sustainability? And that means we have to ask the question, what is it for? And I just want to give you an idea of what is driving us as an industry. And this is not for you to read every little line here. If we go through the 700, or I think it's even more than 1,000 pages of what is written in the Green Deal, you will see these structures. And I've highlighted simply in orange all the numbers here. And what does this tell you? Irrespective of you want more sustainable agriculture, irrespective if you want to be more proficient in energy utilization or in transportation, or if you want to minimize pollution, or finally, and that's why it's called Fit for 55, work on the greenhouse gas emissions going down to 55%. This is all hardwired in targets. And the European Union is writing this down now in dedicated legal documents which will drive the industry. And I would say, wow, are we going to manage all of this? Now, is this a deterrent or is this an opportunity? The message I want to send is here, it's important that academia, but also industries talk with politicians to make them understand, is this really doable? Because you look at these targets, and you want a bit of everything. And that's something that drives us, where we, I think, in our advocacy, I think, need to team up. We talk about gesellschaftlicher Vertrag. It's about understanding whether this is workable, because it needs a lot of effort and a lot of money. But I'm saying for us, it's also an opportunity, but it's a mixed bag here. At the end of the day, we are in line with this, but it's a challenging task. Another one is, and I mentioned it already, you remember that circle with the customer. We want to give the customer choices. And one of the customers, or even the consumer, which is you, have a choice. You can choose between what you buy. And wouldn't it be great if all products had a product carbon footprint telling them how much greenhouse gas is consumed, how much water is consumed, how much chemicals are inside, what good it does for you, but also you have a choice between one and the other. And that's why also with the digital processes we've gone through all of BASF value chains, I have a chart on that in a moment, and given them a carbon footprint, a product carbon footprint. We can give the CO2 kilo per kilo for every product we have, from agrochemical to ethylene. And we can say, well, if you have a better process, you as a customer can choose. And I think that's important, because you will have choices, specifically when it comes to sustainability, because sustainability does not come for free. And specifically if you look at the targets we have. So this is, I think, an important point in terms of messaging to involve the customer and consumer. And then we have 3 pillars, more or less, where we structure our total research and ambition. I'll talk a little bit about the net zero target. Everybody wants to have net zero, no CO2 emissions. We want to recycle our products. The carbon has to come back. That is one pillar as well. And finally, we go through our portfolio, again, Green Deal, and sift out the ones that are, I would call nasty, or are on the list of phasing out, and we want to have the good ones. And you see also we have given ourselves clear targets, numbers, 22 billion euros of sales with the good products, 17 billion euros of circular sales, and of course the net zero target. And I'll talk about the 2 points on the right-hand side more than on the left for simple time reasons. So let's look at the greenhouse gas target. Like every good company, but this is not new to BASF, we strive to reduce our greenhouse gas emissions. And you see, we haven't done a bad job, and we didn't need any regulatory things to do. We moved the last 30 years from 40 million tons of greenhouse gas emissions with a much lower amount of products to around 22 today. We've doubled exactly the amount we produce. And specifically, this means we had a greenhouse gas product carbon footprint, scope 1 and 2, of over 2 tons per ton of product in 1990. Currently, it's around 0.7 on average. And what's the ambition? We want to go to 16 in the next 8 years. And that is hugely ambitious if you consider that we also have growth. We actually need to take the 22 and halve it to 11, and new products actually give you another 5. So the average will be 0.3. So we want to halve the specific footprint of all our products on average. That's the challenge we set ourselves. And as a company, if we put this in writing, this will be audited. That means we have to live up to this challenge. Now, 2050 is a long way down the road, but think about it. Does a company like BASF, with all its production sites, there are 350 worldwide, not emit a single gram of greenhouse gas and still make the products? Do you believe that? Is that possible? Or is it just a technical challenge that maybe is a vision? I would say we have to go for that, but let's first focus on the 2030, which is already tough enough. And I want to give you 1 or 2 ideas where we are moving in this direction and what we can really do. Now I'm talking here to the converted. You are all scientists, chemists, chemical engineers. I don't really have to go through the value chain of chemistry. But this is a proxy in the simple chart of the chemical Verbund. Message here is, whatever we do as a chemical industry, we buy our products out of the mobility, energy, waste, and nutrition market. These are alternative markets. What we then do in a very complex value chain, and BASF is only an example of many for the chemical industry, we crack the products, and when we build them up again to complex chemicals like ibuprofen, amines, Infinity, many more. And then they go to our customer. And most of what we do is actually in the top part, which is the petrochemical value chain based on hydrocarbons. We do some biochemistry, enzymes for example. You see alanine or other enzymes or oleochemicals, and we even interface them with the petrochemical part to make very fancy products like surfactants. And what is new is actually this part in the middle that I really want to highlight. A lot of what we do costs energy. So steam and power, we cannot live without if you want to kind of cook up this cocktail of products along the value chain, because it is an endothermic process to make all this chemistry. So we need steam and power. And I'll come to what that really means in terms of CO2 in a moment. So if we want to change towards NEULAND, new territory, like Christopher Columbus, we can ask the question, do we do more of the same or do we have to change this? And just one last reflection before I go into a few examples. Think about it. Many years ago, 150 years ago, the chemical industry came from green chemistry. We used trees, woods, etc. to do our chemistry. No more, no less. Move to coal, the textile dyes, and even ammonia is produced from coal. Even it is a carbon, we take out the hydrogen and make them ammonia. Then there was a strong, of course, crude oil part, and always we took the leftover out of these alternative industries. Today it's natural gas, and obviously with the Ukraine crisis this is of course a big concern, and I'll tell you why in a moment. But what about the sustainable future? And I try to condense this to simple questions. Question number 1, where does our hydrogen come from? Where does the carbon come from? How do we fix nitrogen, maybe different to ammonia? And where does the energy come from? And we have to detect and see how can we do that, maybe not on our own, but maybe with others. And this is one of the key takeaways in terms of sustainability, because we will not solve this equation on our own. So let's move in this direction now and ask ourselves, how dependent are we exactly on this molecular formula? Big picture, BASF, and this is not Ludwigshafen or anything, this is total BASF. We take 44 million tons of raw materials, mainly hydrocarbons. We add nitrogen and oxygen, water to cool mainly, a little bit goes in chemistry, and we add a lot of energy. 55 terawatt hours is BASF. That's BASF in a nutshell. And if you then say, what is the outcome of this value chain? A volume-weighted average of all products is written here. This is our DNA. We are CH3O, nitrogen, and then chlorine, phosphorus, and so on. So the periodic table of the elements. But we are a carbon company, number one. We are hydrogen need of HCH3, a little bit of oxygen. This is what makes us. Unfortunately, we make a lot of CO2, 22 million tons, as just mentioned. So our goal must be maximize the product, minimize the CO2. Sounds simple. But it isn't simple, and first of all, we can segregate this into two topics, and this is maybe something that we also learned. 50% comes from the chemistry, yield loss, etc. 50% comes from energy. Scope 1 and Scope 2 I'm talking about, right? This is the amount of CO2 we generate simply by heating the whole system up. So exactly those two levers is where we can touch the base to reduce the 22 to 16. And what does it mean if you think about the most ideal carbon source and hydrogen source to go into our Verbund? And it's very clear, if you look at the energy content of the products and also about the right product economy, the CH value, actually methane and natural gas are fantastic. They are high energy. They even give us a hydrogen to spare if you look at CH4, because remember, we need CH3. And we are quite typical for the industry because we're so large. So it's actually best to move from gas to the average BASF product. Otherwise, we would need to put in more energy to come from biomass or other products like ethanol to upgrade this. And if you now try to answer the question that I posed, where does the carbon in the future come from? Where does the hydrogen come from? If it doesn't come from the petrochemical and hydrocarbon sources, which are difficult to get, then we have to think differently. And this is where I want to take you on a journey maybe of what the future may lie. I will not give you all answers, it's just more a food for thought process. This is a busy chart, but I just want to more or less highlight here how maybe different industries can come together. So I'll just take you on that journey. Think about it. If I were to say you're not allowed to take a hydrocarbon, you have to go to your municipal waste company. They actually have hydrocarbons. Why not use them? So a typical waste disposal company today, take Karlsruhe, will be collecting it, keeping your streets clean. That's their business case. What do? They sort this, they take a lot, they incinerate it, they make CO2 because nobody cares for the moment, and then they make energy and give it into the grid. That's their business case. Sounds good. You have a clean street, they make the CO2, you get energy back. But in the future, think about the Green Deal, the CO2 will be something of concern for them. So if they want to change their business model and go into a circular economy and say, oh, we have all this, not waste, but raw material, they would have to find new technologies, gasification, mechanical recycling, solvolysis or pyrolysis, as an alternative. But these are all new chemistries. These are not technology readiness level 9. They are on the lower end. So this is a white spot, number one. Number two, their alternative, if they want to keep the energy, is they can do carbon capture and utilization or sequestration. That would be something that they add on end of the pipe. But what is clear, suddenly a waste collector has new products on their slate. They don't have CO2, they have suddenly syngas. What is a waste collector going to do with the syngas? I mean, for them, it's a product that they can't vent. They have to find a partner. Or they have solids, liquids, and the like. And this is where chemistry comes in from the right. Company like BASF, we can say, well, wonderful, we would love to have those carbon atoms and hydrogens, but we need to interface this with new technologies. For example, fermentation technologies to make what is new raw material for us into the chemical Verbund. But what you are doing here, you are disturbing the system, the chemical system as well as the waste system. And it's very simple. You're taking away energy because you're not burning it to CO2, so you have to replace it by renewable energy. And then the CH ratio doesn't fit anymore to what we need, so you have to add hydrogen. And then you need even more energy. So actually, this disturbing of the system, if you partner, is something that gives you new opportunities and new technologies. And I want to talk about gas fermentation, a little bit about CCU, hydrogen and renewable energy, just for the sake of time, to give you an idea of maybe those challenges that are out there. So first, gas fermentation. We partner as BASF, and we also not only partner, but also invested into the company called LanzaTech. LanzaTech is a company started in New Zealand, now in the US. What they can do, and they have an own proprietary technology that can take these off gases, as I mentioned, out of various different sources and ferment them with an anaerobic fermentation process with the microbe shown here, this Clostridium, and have scaled this to large size production. It works. I'll show you a picture in a moment. The point is really that they can make, for example, ethanol out of off gases. They can also make acetone and isopropanol, and we are working together on products that we like butanol, hexanol, or octanol, with a different bacteria, all to do with modeling and enzyme discovery here. But the point is really, can we use this technology to marry, let's say, the Verbund I showed you? First of all, it's real. This is technology in readiness level 9. This is a plant in Shaogang, China, that LanzaTech has. They have similar plants here in Europe, in Ghent, that are coming on stream. World-scale plants, 45,000 tons of ethanol made from off gases. So this is real, and we say, how can we now bring the logic of these technologies together? And the simple thing is, we have the syngas, we have CO2 necessarily, we gas ferment this, we can then dehydrogenate the ethanol to ethylene, and then wonderful, we have an input into our value chain. Sounds simple. And all of this is actually possible if we were to put this together and we add a little bit of hydrogen. So all technologies are there, and I have one chart now to say, what does it really mean if we do this? So I asked the question, how much waste do we need for municipal waste, let's say in Karlsruhe, which would probably be around the 370 metric tons of waste that is made by all of us. You collect it, you burn it, you keep the energy, you add hydrogen, as you can see here, from electrolysis, you need around 50 kT. You put it into the gas fermentation with a little bit of reverse water gas shift, and you make ethanol, and then endothermically you make ethylene, 100,000 tons. Simple mathematics, if you were to do this, all technologies are possible, we could build it today. And the answer is really that it's a huge power demand, specifically because you need so much hydrogen with electrolysis. You need 3 terawatt hours of energy to make 100,000 tons of ethylene. You would say, is this a viable, sustainable option? We'd say, nobody will pay for it. Because today, a steam cracker only needs around a fifth or a sixth of this, and then it's affordable. And then the question to you would be, product carbon footprint, 0, CO2. It's actually coming from your own waste. Are you willing to pay? That would be the question, actually, the challenges we have. But where this leads us is to the question where the big pain point is the hydrogen. It's not the technology up there, that's not okay, it's the hydrogen. And that's why 2 words on hydrogen. Hydrogen. First of all, big picture. Worldwide, there are different numbers, but roughly 74 million tons of hydrogen are made. And they are the reason, it's one of the largest producers of anthropogenic CO2, because the process is actually very CO2 intense, steam methane reforming, or even with coal, it's worse. Over 700 million tons, most probably close to 800. And most of this, as you can see, goes into ammonia, refineries, methanol, and then the huge breadth of all chemistries that we have. Without hydrogen, we cannot live. It's most important. But what you do not see here, because people talk about e-fuels, they talk about fuel cells, nobody currently uses hydrogen in this, has no market, because it's so valuable. The hydrogen is better as a product than as something to be burned. But another point is for us, because it's so much CO2, we need at BASF 1 million tons. We're a big player here. We produce half of it ourselves, the other half we buy. So if we have a CO2-free hydrogen process, that would be great. That really helps our CO2 balance. But even worse, and this is not a BASF topic, it's a chemical topic, a lot of the hydrogen that goes into ammonia is actually wasted, I would say, because it is oxidized again to nitric acid or HCN. And I come to that example in a moment to say, what does that mean for new innovation challenges? One chart on making hydrogen, I show this a couple of times. This simple diagram, CO2 reduction potential by electrification versus energy cost efficiency. Start at the bottom, steam methane reforming. I already mentioned this, 10 times the amount of CO2 per hydrogen is the balance with a reasonable amount of energy put in. Alternatives, if you want to go CO2-free and electrically, you can do, I think everybody knows, water electrolysis. You're not going to get around the thermodynamics of this reaction. You can do it very cost-intensive, but you will always need 55 megawatt hours because that's the thermodynamic limit, which means it's CO2-free, but you need huge amounts of energy. I just showed you the example with the calculation for the 100,000 tons of ethylene. Or the methane pyrolysis, and this is the one that we bet on at the moment because we are developing this in a special moving bed reactor that is electrically heated, but it's CO2-free. And I would say it's a good balance of CO2-free, electrically heated, and a reasonable amount of energy because it's always endothermic. And sustainability is not only about the CO2, you see it on the right, and that chart is here, CO2 price against production costs. The SMR is the gray line, that is the baseline and our benchmark. Electrolysis, simply because of the energy demand, now taking German prices, is x-fold higher. And it also has a gradient because the current energy mix in Germany has a lot of CO2 still. So the more you need and the higher the CO2 is, the more expensive. And the methane pyrolysis, as you see, fits in nicely with a bartering off of the hydrogen you get and the carbon you get, because 1 ton of hydrogen gives you 3 tons of carbon that you can use, of course, sustainably, because it also has a market. So we see this as a new technology, and we are, of course, working on this. I actually talked about it last time I was here in Karlsruhe. So making hydrogen efficiently, one way of solving the problem here and going to CO2 neutral or CO2 free processes by substituting the SMR. And I just want to lead you on some chemistry here. Remember I said a lot of the hydrogen is used, let's say, not very intelligently. And just walk you through this. Think about it. You do an SMR, methane and water or steam make hydrogen. Then the Haber-Bosch process makes ammonia. And what do we do then? 5 million tons of hydrogen equivalents, a lot of ammonia, about 30 million tons, are oxidized in the Ostwald process to make nitric oxide that makes HNO3 that makes fertilizers, ammonium nitrate. And look at about the hydrogen balance. We have all the hydrogen from methane and water ends up in 12 water. Because we've gone up and down the energy cycle, I would say that is workable, but not very intelligent. Energy-wise, a disaster. But we need the ammonium nitrate, don't we? So we've gone this way, and it's state-of-the-art. Challenge to everybody, why don't we take nitrogen and oxygen and fix it directly? It's so simple if you write it down. You don't need all the hydrogen. Why go all this circumvent that way and do it this way? Now you would say, is this easy? If someone hadn't thought about it, there's a Berkland-Ide process many years ago, and they all say technically challenging to do this. But if I were a scientist, this would be great to work on. Another one, similar, HCN, very important molecule for many things you do, and also we do. Similar logic, SMR, Haber-Bosch, ammonia, Andrusov process, state-of-the-art, oxygen, methane makes 6 to 24 water, and then you get a bit of HCN. Again, product economy disaster, why not do it differently? Nitrogen, methane, you made HCN and hydrogen. Yes, it's endothermic, you might need plasma technology, but wouldn't this be really great? So I give this as a challenge, more or less, out for sustainability. But this is where we have to think, yeah? So we have to go through our old processes and go into a new world, NEULAND, if you like, exactly with these challenges. I wanted to talk about carbon capture and storage and maybe some alternatives. And yes, this is one chart on that we also see carbon capture and storage as an alternative to really do something until 2030, because it's doable. And in Antwerp, for example, where we're a large site, Antwerp has about 3.6 million tons of CO2 as an emission. We can collect this out of our ammonia process, out of our ethylene oxide process with our own technology, sequester it, gather it, put it into terminals, and then via ship or pipeline, still to be decided, move it off to the North Sea. Northern Lights is the topic here. There are areas that, from a geoformation, can easily take the CO2. And we've done the calculation together with partners here, in this case Air Liquide and others, And that gives a great opportunity to sequester 1 million tons per year in Antwerp. And finally, in the final stage, make Antwerp actually net zero. A huge production site for BASF. 3.6 million tons of CO2 are possible. And this one is really affordable because the blue hydrogen that you get out of this actually is only an addition of around 100 euros per ton of CO2 to make this operational. And that's why we also say this is part of the solution, because we cannot get all the new technologies, the one I just pointed out, so quickly. But the answer is to the CO2 question now. And obviously, we are asking here, and it's important also for a funded project, there are many, many applicants, and we actually got here the ask to make this into a common grant. One way of sequestering CCU. Let's talk about a different technology, which would be the carbon capture with metal organic frameworks. MOFs. So off-gas from, for example, cement industry can be sequestered with molecular organic frameworks. They are wonderful because they have a high absorption rate for CO2 and they are not sensitive to hydrolysis. And Svante, a startup in Canada, has mastered this technology in these frames by coating them, stacking them like a heat exchanger, and then they put them into these big machines here called RAMs, rotating absorption machine, and they can then sequester the gas out of cement works. And it works. In 60 seconds they can do a cycle, absorbent, desorption with water. The magic is this MOF, this zinc triazolate oxalate that we make, and the beauty is we don't make it as a laboratory curiosity in gram scales, because MOFs are still very special. We make it in tons. So we scale this, and this is exactly where, of course, group research can do things. We have the facilities I showed you, and we can scale this together and get this into production. And this is working, for example, in Vancouver in a site to sequester the CO2 out of cement from a home chem plant. And it's really nice that actually we partner here and show that we can build these molecules, make them large, and of course the other company has a benefit, and I think the society has a benefit that this works. So this is new technology where you need to bring in the partners together. Last point I want to make, heat pumps, electricity. If you draw a big box around BASF Ludwigshafen, just 50 kilometers from here, and ask about the energy cycle, 20 terawatt hours of energy go into this large site. We actually make 8 terawatt hours simply by the exothermic chemistry, so we have 28 terawatt hours to cool. We do that with the River Rhine and with the heat fin fans. 8 terawatt of air cooling with a lot of energy. Again, you ask, is this intelligent? But it's the only way to do it, because we have to get rid of the energy we put in. And 6 is actually diffuse loss. More intelligently, why not take renewable energy and take our low-grade steams and upgrade them again to usable ones? Because we don't like 80-degree steam, we want 150 plus. And again, it's a renewable energy question, and 2 examples here. Our acetylene plant on the left produces a lot of off-steam that is probably currently cooled. We can, with a Siemens Energy heat pump, put in energy and then sequester or avoid 160,000 tons of CO2. All the collected off streams of all our lower grade steam can be managed with MAN energy solutions. And you see here a heat pump of enormous size. You see this little person here on the left. Huge, is the biggest heat pump in the world that we want to build in Ludwigshafen. Chance 400,000 tons of CO2. So the question, can we really do it? With this technology, yes. But this is again the way to go. But one thing is clear, you will not be doing this without renewable energy. Whatever you do, the methane pyrolysis, the electrolysis, this technology you will need to master endothermic processes. And that means we have to go into one thing, a new source. I asked the question, where does the energy come from? It comes from renewable energies, and obviously BASF is investing into new offshore wind parks such as this one. And just my last or second to last chart, here we partner together with Ørsted, Vattenfall, and invest directly into offshore wind parks, because we need this as a source. And you see here on this chart, without going into detail, we want to greenify the electricity demand of BASF. And this is a global picture, currently very gray. With the growth we have anticipated and the more electricity we need, it will go up, 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 up. but our ambition is clear. It will only be based on green energy in the future. And that's why we invest here. And that makes a lot of sense, and we convert this then into chemistry. Point is here, there will be huge competition for this energy, and this is going to be the driver of all industry, because you can solve a lot of the problems we have with green energy. That means electromobility always is one, but also cement industry, steel industry, they all will be vying for this material. So the earlier you invest, the better. And that's why strategically it makes a lot of sense. So I wrap up. Innovation drives sustainability, sustainability drives innovation. It all fits together. I could only give you a few examples, a little bit how we do research, what our focus is, the purpose, and some examples. It will be interdisciplinary. You can't do this on your own. You need new technologies, the intelligent conversion of green energy, the KPI, I would say, megawatt hours per ton of saved CO2 is what drives us. And it will be about partnerships with academia, because without academia and some fundamental knowledge, without the partners, Ørsted, Vattenfall, Lanzatec, Svante, Air Liquide, you heard them all, and just a few, we will not be managing this on our own. So our way of doing this will be together, because that I think is part of innovation. And yes, we will also do this digitally and with a lot of automation. And you see here that there are enough challenges out there to keep, I think, the chemical and engineering faculties alive for many years. I'm 100% sure. So thank you for bearing with me, and I'm happy to take, if there is time, 1 or 2 questions. So thanks a lot.
Thank you very much. Ganz herzlichen Dank. Auch hier nochmal die Einladung, auch Sie gerne eine Frage stellen, entweder in Slido oder aber wir haben auch ein Mikrofon. Ich komme gleich nochmal auf Sie zurück. Sie können sie ja im Geiste schon mal formulieren. We have one question from the chat. Was CO2 only reduced by not emitting or also by compensation? I think a little bit you already answered, but maybe you can tell more.
In the past, now, I guess
Yes.
this question is,
Yeah.
I mean, up to now, we have not sequestered anything. That was the question. No, not at all. But that is going to come in the future, because we cannot really do the big move in the future to do so. Most of it is simply by better technology, operational excellence, and reducing consumption and yields. That is the 20 million tons we've done so far. But we need a new step now.
Okay, thank you. Es gibt weiterhin die Möglichkeit, noch Fragen zu stellen. Ich switche jetzt auch ins Deutsche. Vielleicht ist die Hemmschwelle dann für viele auch niedriger. Hat jemand eine Frage? Oder anders, wer hat eine Frage? Okay, momentan gibt es hier keine, aber wir sind zu zweit und wir haben beide noch welche, aber beginnen Sie gerne.
Nutze ich die Gelegenheit, noch eine Frage zu stellen. Also zunächst mal vielen Dank auch, dass wir für die Zukunft der Chemie und der Verfahrenstechnik auch in den Hochschulen noch viel zu tun haben werden. Das ist ja prima zu hören. Ich hätte aber noch eine Frage. Es waren jetzt viele Prozesse dabei, viele Technologien. Ich habe mir die Frage gestellt, wenn man die Bilder gesehen hat, hat sich das ja doch noch ein bisschen an der historischen Verbundstruktur eigentlich orientiert. Die Frage wäre eigentlich, hat der Verbund und der Verbundstandort noch Zukunft und werden wir den in 50 Jahren noch haben? Oder werden sich die Chemiestandorte dorthin verändern und sich dorthin bewegen, wo die Energie bereitgestellt wird? Ich denke jetzt an Projekte, die wir gerade machen, Wasserstoff auf der Plattform zu produzieren, wo die Windkraftanlage steht. Das ist eine Frage, mit der wir uns beschäftigen, und da würde ich jetzt gerne mal die Antwort der BASF drauf hören.
Also die Antwort ist beides, aber ich würde sagen, wir werden ohne eine Verbundstruktur nicht auskommen. Simple Größenordnung. Ich glaube, Leute vergessen oft, dass es ja nicht um kleine Mengen geht. Wir reden in Terawattstunden. Wir reden in Kilotonnen, nicht in Tonnen und Gramm. Das heißt also, eine intelligente Struktur wird immer eine Verbundstruktur haben. Ja. Und ich habe ja gar nicht darüber gesagt, dass die Tatsache, dass wir schon sehr viel Wärmeintegration haben, spart so viel CO2, das würde ich ja alles aufgeben, wenn ich dezentralisiere. Ja. So. Das heißt also, meine Antwort da ist ja, Verbundstandorte, Petrochemiestandorte werden bleiben. Ja. Aber es wird Business Cases geben, wo ich die dezentrale eingesammelte Energie auch benutzen kann, und das sollte man auch tun. Okay. Dann habe ich auch meist den Luxus, und den habe ich oft nicht, Überschussenergie zu haben, und Sie haben gesagt, was mache ich jetzt damit? Da kann ich auch relativ ineffiziente Technologien machen, aber das ist nicht schlecht gemeint, sondern ich kann sie nutzen. Aber den Luxus, ich sage mal, die eigentlich groß gesammelte Energie zu verschwenden, den werden wir nicht mehr haben. Das wird es nicht geben. Also es wird beides geben.
Okay.
Und ich habe nichts dagegen gegen modulare Technologien, wird es auch geben. Nur für die großen Lösungen, die wir haben, mit den 55 Milliarden Tonnen CO2, das kriegen wir nur hin in solchen Standorten.
Gut, haben wir noch eine Frage aus dem Publikum? Nein. Dann an dieser Stelle ganz herzlichen Dank im Hinblick auf die Zeit. Herzlichen Dank für dieses interessante Keynote, auch an Ihre Frage, Herr Hirt, und nochmal einen Applaus bitte für Detlef Kratz. Dankeschön. Danke. Danke.